Welcome everybody to our webinar today, Elevate Your CFD, Discover TwinMesh 2026 for Rotary Positive Displacement Machines. My name is Anusha Zegami. I'm part of the technical sales team, and I will be moderating our webinar today. And my colleague Jan Hesse will then later tell you everything about TwinMesh. If you have any questions, if any questions come up, feel free to ask them anytime during our webinar, and then at the end we will answer them. Jan, can you maybe move to the next slide? Thank you. So before we begin, a small introduction to us. We are CFX Berlin. We are experts in numerical simulations in over 25 years. We are 18 employees at Berlin, most of which are engineers or physicists. And we mainly offer software, mainly Siemens software, but we also have our own creation, which is TwinMesh, and more specialized software, which is Flownex and ParticleWorks. We offer hardware for the software that we sell and consulting and training. We also do simulation and optimization, and we also have a small research and development department. And we have been with ANSYS for over 20 years, but we decided to change to Siemens in 2024 because we believe that Siemens offers the better solutions. That's why I also want to use this opportunity and tell you a little bit about our licensing model at Siemens, which is kind of the all-inclusive solution of the simulation world. Because with one license, you can get access to 4 different simulation programs, one of which being STAR-CCM+, which is our CFD software, AMISM, which is simulation on a system level, SimCenter 3D, which is for structural mechanics, and HEATS, which is for optimization. And apart from the big advantage that you can gain access to all of these different programs, there are also other advantages to the SimCenter X Advanced model, which is, for example, that you can open unlimited instances, that you have no extra costs for global licenses, and of course that you get very good support from us. And yeah, that's it for the small introduction. Now I will hand over to my colleague Jan Hesse, who will tell you about TwinMesh now.
Okay, so then let me start. So yeah, now let me introduce TwinMesh. So TwinMesh was developed by CFX Berlin to enable high quality CFD for rotary positive displacement machines, for example, for screw compressors or gear pumps or lobe blowers. And it brings all the required steps into one unified end-to-end workflow so users can work efficient and focus on the physics instead of manual meshing and repetitive CFD setup tasks. The workflow consists of 3 main steps. So at first, the cut import to extract the fluid volume and divide it into the stator part and the working chamber part, like you can see here on the flow from the left side. The next step is the meshing, where the stator mesh is generated. So you can use any meshing tool you have, for example, in SimCenter STAR-CCM Plus or in ANSYS products. And the working chamber mesh is generated by TwinMesh, and it used the specialized meshing strategy, which I will discuss later. After that, TwinMesh will export a full setup. So you can start your simulation right after exporting all the meshes and the setup, because the CFD setup will also be available then. So the next thing, where is TwinMesh used? So TwinMesh is used across a range of rotary positive displacement application. So the key areas include screw compressors and expanders, screw vacuum pumps, gear pumps, gerotor pumps, and a lot of more. And so we are proud to support leading companies working in these applications. So many of our clients have used TwinMesh for years and value its reliability and efficiency. So on the right-hand side, you can see some of our customers which are using TwinMesh right now. So what are the challenges? So the question is why we need TwinMesh. So let me illustrate this with a screw compressor, as you shown on the right. The compressor is cut open so you can see the working chamber. There are two intermeshing rotors. And due to the rotational motion, the flow volume changes continuously. Additionally, there are very thin clearances between the rotors and between the rotors and the housing in both radial and axial directions. Because the flow volume is time varying, a transient simulation is required. The fluid behavior can be complex in compressors. Compressibility is essential and with high pressure and temperature, so real gas effects become important. In pumps, cavitation must be considered. On the other side, there is a interest in structural. So, for example, thermal deformation affects clearances, which could lead to leakage losses. Altogether, these factors impose specific requirements on the CFD. So now let's look at the discretization options for the flow domain and why TwinMesh is needed. There are several meshing approaches, each with different strengths and limitations. The first one is overlapping meshes. Could be that you know this type of mesh or meshing approach. It's also called immersed boundary or overset. And here for the immersed solid approach, a background mesh represents the working chamber. So here in this case, the background mesh is the blue one. And you have in the foreground a mesh which describes the rotor solid. So this is the orange part. And during the simulation, the rotor mesh rotates. So in this case, the solver determines the overlapping volume, applies momentum sources, or combines the meshes to calculate the impact of the rotor motion to the fluid. This meshing is simple, but there are drawbacks. For example, the near wall accuracy is limited. Boundary layer effects are hard to capture without fine cells. And the model becomes large. Runtimes increase and the stability issues can occur. So that's why we go to the next type of meshing, so which could be remeshing. With remeshing, a new mesh is automatically generated as the geometry evolves, resolving the domain at each time step. Accurate small radial axial clearance require very fine resolution and often extremely small time steps to maintain the mesh quality. This could lead to high computational cost. Using the next one, which is also used by TwinMesh, is called mesh deformation. In this case, the mesh topology remains fixed. Only the node position are updated each time step to follow the rotor motion. So this can deliver efficient calculations, good gap resolution, and full model support. However, creating a suitable deformable mesh for complex clearances typically demands significant manual effort. And this is precisely where TwinMesh helps by automating working chamber meshing. And that's why we developed TwinMesh. It uses the mesh deformation approach, as I said, and automates the meshing process. As you can see in the animation on the right, TwinMesh pre-computes the node position for each or for every time step before the CFD run. And this ensures consistent meshing quality throughout the motion. It generates high quality hexahedral meshes tailored to narrow clearances. And on the animation, you can also see some red markers, which indicates the control nodes. Yeah, so the topology of the mesh keeps the same, only the nodes are moving while the simulation is running. And during the simulation, the solver reads per time step files with the updated node position. Yeah, so the mesh will be created before the simulation run, and then you have a lot of files, and the solver will import these files while the CFD solver is running. Okay, this was a short overview, and let me briefly summarize the main advantages of using TwinMesh. First, as I said, we have high quality hexahedral meshes, which accurately capture the working chamber and the thin clearances. Yeah, so the stator mesh before the working chamber and behind the working chamber is meshed with a standard meshing approach, but the working chamber is meshed by TwinMesh. And TwinMesh pre-computes the node position for all time steps, ensuring consistent quality before the CFD run. Yeah, which is essential because in other approaches, normally the solver will calculate the mesh quality or will generate the mesh while the solver is running. And then it could be that the mesh quality goes down and the solver can crash. So this is not important with this approach because the mesh quality will be checked before the solver run. In combination with Siemens SimCenter STAR-CCM Plus, this enables fast, stable, and reliable transient simulation. To automate the workflow, TwinMesh provides a ready-to-use template for the setup and also for the post-processing. And so you can go from cut to the results very quickly. So now let me take a look at how TwinMesh works in action. So here you can see the mesh of the working chamber generated in TwinMesh. In this short video, you will see the workflow and how the software simplifies the process for our clients. TwinMesh integrates seamlessly with Siemens SimCenter STAR-CCM and also for ANSYS. We start by creating a new TwinMesh project. From this TwinMesh project, we launch Siemens SimCenter STAR-CCM Plus to prepare the geometry in STAR-CCM Plus. We extract the fluid domain, split it into the stator and the working chamber, and generate the stator mesh using STAR-CCM Plus meshing. Next, we export the rotor curve, so the profiles from STAR-CCM Plus, and import them into TwinMesh. In TwinMesh, we define the machine-specific parameters and the meshing settings, and then generate the working chamber mesh and check its quality. TwinMesh export all meshes, as well as a macro template for the CFD setup and selected post-processing tasks. Once the CFD setup is complete, you can start the simulation run right away and review the predefined plots and scenes. So this was a little bit quick. After this webinar, I will show you how it looks like directly. Okay, so now I'd like to show some simulation results that illustrates a typical task and user benefits. So at first, for example, you can use TwinMesh for rotor design. With TwinMesh, you can modify rotor geometry to assess its impact on machine behavior, covering performance, cavitation risks, and leakage. Likewise, you can modify the housing to study how inlet and discharge flow affect the efficiency. So for example, pressure losses or pulsation. Both examples here are lobe pumps. In this example from Hugo Vogelsang, the inlet geometry was varied to quantify its effect on efficiency. In addition to visualizing the flow field with the volume, within the volume, time-resolved information is necessary in order to compare the results with the measurements or to better understand the effect of pulsation or noise emission. Yeah, so this is the standard approach. You can export time-resolved pressure, mass flow at inlet and outlet, at clearances, and so on, to find out how they match to the measurement data. So here you can see two animations of the velocity field. First in the gerotor on the left side and on the right-hand side in a lobe pump. Elevated velocity in the thin clearances highlight leakage flow path, which reduce volumetric efficiency. And so with this results, you can find out where are the losses, and so you can modify your geometry, repeat your simulation, and have a look at all the result data to find out what is the best, the best geometry for in your case. On the compressor side, we show here a screw compressor and a screw vacuum pump. So the screw compressor on the left side is here simulated with a single-phase gas model. For the oil injected part, I will another slide, a slice on you will see on the next slide. The rotors in both machines can feature high wrap angles or even variable pitch, which raises demands on the meshing, but TwinMesh can handle this. And here you can see an animation of a simplified scroll compressor. So one scroll orbits around the center while the other remains fixed, forming a moving pocket. And gas is progressively compressed as the pocket moves inwards toward the central discharge port. So this is only a simple tutorial example, but normally it looks a little bit more complex. And finally, the more complex application is the simulation of an oil-injected screw compressor. So here in SimCenter STAR-CCM, it offers a wide range of numerical models that can represent the different regimes within the working chamber. So one particular efficient option is the mixture multi-phase model, which allows calculation to be performed as quickly as possible on a coarser mesh. The mesh resolution and time step can therefore be adapted to the available computing resources, which further increase the accuracy of the results. The phase interface is handled here using an LSI and ADIS, which can be used to control how the phase interface is represented. So on the right-hand side, you can see there the oil, which is coming into the working chamber. We have on the top and on the bottom side, which is not seen here, but we have two inlets, oil inlets. This simulation starts without oil, and then you can see how the oil is moving by the rotors. You can see the sealing line, so where the oil is located along the tips. And yeah, so with this case, you can try to optimize the location of the inlet pipes and have a look at the efficiency of the pump. So in STAR-CCM Plus, there are also some additional models which are not used yet, or in this case, but it's also possible to use a film MMP. So this allows thin layers along the wall, which cannot be resolved by the mesh. And so in this case, you can do simulation to see what happens along the casing wall and how the wall film changes with time and affects the gap flow. Another thing is you can also couple this mixture model with a Lagrangian model. So for example, if you have a flow where you have droplets, then sometimes it's important to see also the droplet path in the simulation. And this is also possible, but not used in this case. So, but that's not all. So here's some additional twin mesh capabilities. If you have rotor deformation data, for example, from a structure mechanical simulation, you can import this information by bending line or by thermal expansion. So TwinMesh is can handle STL files which coming out of your structure mechanical simulation. So you can see how is the impact of your deformation on the gap size and what is the effect on your efficiency of your machine. So for multi-stage machines, you can combine different twin mesh projects into a single simulation. So for example, on the right-hand side, where we have a multi-stage lobe pump, the rotor profile is the same, but the chamber width is different. And then you can use twin mesh different twin mesh projects and put it into one simulation. For scroll compressors, you can also include reed valves, preventing backflow into the working chamber. And yeah, we are constantly enhancing twin mesh and adding new capabilities to meet our customers' evolving needs. So now let me show or explain some new features in twin mesh. So in twin mesh 2026, the main focus has been on the automating the workflow with the goal of integrating twin mesh into the work process and thus reducing manual effort. So furthermore, it also reduces the risk of errors caused by incorrect input. As a result, the entire process can be accelerated, increasing the overall output. Yeah, so it's impossible to use twin mesh without the GUI. Generating the meshes, put it into the workflow you have, and do a lot of simulations. This workflow also need a possibility to define the setup of twin mesh, not with the user interface, but with a file. And that's why it's possible to import into twin mesh or export out of twin mesh XML files, which will have the information of the current setup. And so you can manually change these setup in a file and use it with your new project now. What you also do for every new release, we try to increase the mesh quality. In this case, we have increased the post moving to have high quality meshes, especially near sharp edges. This is mainly used for highly wrapped machines, for example, for vacuum pumps. There are also many other additional features, for example, new options for modeling eccentric screw pumps, more flexibility for the interface generation, and advanced setup definition. So this enhancement makes TwinMesh more versatile and user-friendly across a wide range of application. So before I finish my presentation, I will give you some upcoming features of the next release. So the main focus was on giving an automated workflow for multi-stage cases. So in the previous version, you have the possibility to do a multi-phase setup, a multi-stage setup, but this was mostly manually in the CFD setup. And now it's possible to export the full setup for this multi-stage roots pump, for example, but also for other types, for multi-stage compressors or screw spindle pumps with different rotor profiles or gear systems. So it's very easy to set up the CFD with this new feature. And some more extended mesh quality options to show the mesh quality inside TwinMesh, and also increased meshing speed, export, and quality. Okay, so this was my presentation. If you have, if you want more information, you can go to our website. There's the twinmesh.com, and also on the YouTube channel. So there are a lot of other animations there where you can see how TwinMesh works. And but if you have more questions, you can also contact us. You can contact Anusha, or you can contact me. Yeah. Okay.
Yes, thank you. Thank you for your attention also from my side. Jan, I'm seeing questions too. The first one is, for the multi-stage simulations, are you able to include the intercooler?
Yes, you can include in the CFD simulation every cooling system you have. You have to add your your solid of your machine, and then you can introduce a single or another physic where you have your cooling system around your working chamber, or
Then,
where you have it.
thank you. I'm also seeing a question about the costs. For that, we can definitely talk on the phone in the near future, today, tomorrow. That's a bit more complicated, and yeah, I can definitely explain that on the phone, or via email. Then another technical question: how much mesh can be fine at clearances? Not sure how far. Maybe
how
the
fine the
question
mesh?
fine.
Yeah, so the standard value for our mesh in clearances is 20 elements. Over the clearance. And this is not limited by TwinMesh. It's only limited by the solver. So if you have more elements in the clearance, then the aspect ratios increases, and so the solver could be more unstable with this. So if you have more elements in the gaps, then you normally have also more elements in circumferential direction. So the overall mesh size increases, and the computational effort increases. But in TwinMesh, there is no restriction. You can go down to 1 micron, depending on your rotor profile. So you can also nearly close the gap. It's not possible to close it fully because the TwinMesh approach needs a mesh in the radial gap. Yeah.
Then a question if it's also supported with ANSYS Fluent, which it is, right?
Yeah, it's also supported with ANSYS Fluent, but we think ANSYS Fluent is not good for this approach because it has the problems with high aspect ratios. And so in our previous time where we use ANSYS for this, there was, I think, only 2 or 3 projects where we used it. And it was really difficult to keep it stable and to run it. And that's why we used always ANSYS CFX in that time, which is more stable for this application. And now we are switched to SimCenter Siemens STAR-CCM, and where you have more possibilities and also more influence on the stability of the simulation run.
Then a long question, is it possible to simulate a complete screw pump, including the valve, to evaluate values as peak and closing pressure based on a predefined stiffness for the valve region during the pump operation to simulate a real condition?
Yes, and normally you can do the simulation like you want. So it's possible. In TwinMesh, the automated setup is only for the standard approach. So for example, you specify an inlet and outlet pressure, the temperature at inlet, the revolution speed, and then TwinMesh will generate the setup for this. So connect all the meshes together, define all the interfaces, and so on. And for more simulation, so what you can put on in the outlet, so additional valves and so on. This is not included in the standard output of TwinMesh, but you have the possibility to do it after exporting or after generating the setup out of TwinMesh. You can change what you want in the CFD setup and add additional models or additional geometry to this.
And the next question, there are a lot of questions. 20 cells beside the prism layers. I'm not sure what.
Yeah,
Yeah,
20 elements in the gap, so in the radial gap, and TwinMesh can also generate the actual gap meshes. Genau, right, and these 20 elements also used for the general working chamber. Yeah, so you have every time 20 elements in radial direction, and these 20 elements are squeezed together in the gaps and expanded between the lobes. Yeah.
Thank you. Then the next question is, are you or have you done real valve simulations using FSI with TwinMesh and your flow solver?
Yes, we have done simulations. So we have done simulation with ANSYS and also with STAR-CCM Plus. So there is the possibility to use different approaches. The complex approach to combine TwinMesh with a full FSI coupling model. So we find out this is too complex. So normally our approach is before we do the CFD simulation, structure simulation with the valve, find out what is the behavior depending on the forces on these valve, and then we can use this information inside TwinMesh to model, inside the CFD simulation to model the movement of the valve. So the movement of the valve is not a full FSI simulation. It's a modeled movement depending on the forces which are acting on this valve. And this works very well because you have not this complex FSI coupling, and you can do the simulation run like you have, and it's really fast, and it works fine.
Then I have two questions about licenses. First of all, can you explain about global licenses? I'm not sure what the question means. If you mean for the Siemens software, then it's free of extra charge. And for TwinMesh as well, as far as I know, I'm not 100% sure on this. We would have to email for that question. But yeah, I'm also not generally sure what you mean by that. And then you asked another question, do you have a student license like STAR-CCM Plus? We do not offer student licenses, but we do offer licenses for shorter periods of time. And of course, we can give a little bit of discount, so the prices, yeah, we can talk about the prices definitely. Then another technical question, do you suggest a common computational mesh for both CFD and acoustic analysis or separate meshes optimized for each physics? If separate, how is data transferred between the two meshes and what are the associated accuracy considerations?
I think so. When we do acoustic simulation, for example, for a screw compressor, then this is the same approach like we have here. The working chamber mesh is meshed by TwinMesh, and the stator mesh is meshed by any meshing tool. And then we, for example, if you have an acoustic silencer behind your screw compressor, then we model also the volume before the acoustic silence and behind that. And the mesh size depends on the pulsations you will see. But it could be that it's a little bit finer, but normally it's the same approach, but depends a little bit on the pressures you will see. So in some approaches, we have seen that it could be that you have to decrease your time step and increase your mesh size to see the fluctuations, the pressure pulsations in the simulation. If you have a larger time step, then sometimes you cannot see these pulsations correctly. Yeah, but this is so like in every simulation, it depends on your case, and then you have to refine your mesh. Yeah.
Then the next question, in screw compressor simulation using TwinMesh, can we select any time step to match the current number? Is the solver taking care?
Okay, can you repeat?
Yeah. In screw compressor simulations using TwinMesh, can we select any time step to match the current number? Is it solver taking care?
So in combination with TwinMesh, the solver time step depends on the number of meshes you have generated and the rotational speeds you have. So the general approach is that your time step is defined by your your angle step. So the how many meshes you have generated for each rotation. And this limits a little bit your time step. So if you want to use smaller time steps, then you have to use more meshes per rotation. There is also a possibility, it's called spline interpolation, where you can generate meshes only for example, 1 degree step. And then TwinMesh will interpolate between these meshes to generate meshes in between. And this is more, in this case, you can handle more or smaller time steps without generating so many meshes. But the normal approach is you generate more meshes and then you can decrease your time step.
Another question about the time steps. Can smaller time steps be used in the simulation than the time step for which the mesh was generated?
Yeah, it's the same. So it's the same answer. The time step depends on the generated meshes and can only be handled with more meshes. if you decrease the time step. Yeah.
Thank you. Then, is TwinMesh compatible with COMSOL? Specifically, can TwinMesh generated meshes and results be imported into COMSOL? And do you have any experience or recommended workflow for using TwinMesh together with COMSOL?
No, at the moment, no. So we haven't worked with COMSOL, only with ANSYS CFD and STAR-CCM Plus at the moment. So there is at the moment no tool available where you can import the exported meshes from TwinMesh into the COMSOL CFD.
About multi-phase simulations, how much accuracy or match can we expect? Are there any case studies?
Yeah, this is a good question because the multi-phase simulation, for example, oil injected screw compressor, is still in working progress. So we stepwise. So the visualization of the the flow of the oil inside the screw compressor, for example, looks good at the moment. We are now at the case that we will compare these simulation results with customers. So for the ANSYS part, we have also compared the results with customers and works very well. Now we are comparing the Siemens SimCenter STAR-CCM results, which looks nearly the same, but we will also compare this in more detail. Yeah, but as I said, it's still in progress to get good results because, as you know, the regimes in such a machines are really different, and to handle all these effects inside the machine could be challenging. And so that's why I cannot say what is the quality of the results right now with a number.
And can positive displacement machine simulations be run in SimCenter STAR-CCM Plus using the GPU card?
So I think the problem at the moment is that moving mesh is not supported by GPU, and that's why I think this part is not supported for GPU. But as I heard, they are on to develop it. But at the moment, I think there is a limitation there. Yeah. For the standard approaches for standard simulation, you can use GPU, but I think for moving mesh, there's a limitation.
And do you have benchmarking of CFD results with test results? Can you please share if you have any?
So for our test results, we have a lot of papers on our web page, so twinmesh.com. There you have to go to the blog post, and there are a lot of papers where you can see the results of TwinMesh in comparison to measurements. Yeah, so there you can download everything.
Perfect, thank you. And then last question I'm seeing: do we need both TwinMesh and STAR-CCM Plus license on the same machine? Is it possible to use computational servers only for running STAR-CCM runs and use separate machine to mesh using TwinMesh?
Yeah, it's possible. TwinMesh license server is different to the STAR-CCM server. You can have, for example, a local TwinMesh license server. The only thing is that your simulation server has to have a connection to the TwinMesh license server, because while the simulation is running, TwinMesh or the solver will also check out a license to run the simulation. Yeah, so that you have a connection. The license server can be different on different locations, but they have to have the way to the TwinMesh license.
then I saw actually another one. How do you deal with thermal timescale mismatch between the solid and fluid in CHT?
Yeah, so there are different approaches. So in ANSYS, there is the approach to use different timescales. So for the fluid timescale, you need to have a smaller time step. For the solid, you, for example, use a factor of 1,000 to do it to get a really fast temperature field there. The problem is then, yeah, if you have a large time step in the solid, then the temperature is smeared out, so that it could be that it's not the correct one. And so, yeah, the normal way is to start with the large time step and decrease time step over some revolutions to get a nearly steady state temperature field in the solid. And for STAR-CCM Plus is a nearly same thing. It is not via a time step; it's via another. It's another way there, but it's possible to handle different timescales.
Okay, so that was the last question. Thank you very much for your attention. And if any other questions should come up, especially also regarding costs and licenses, please do not hesitate to reach out to us via my mail. And yeah,
At the
have a
moment,
nice
as so
day.
what I can do right now, it's only if they are interested in. I can show shortly how TwinMesh looks like. Only for these guys who wants to see it. The other guys who knows it, then not. But so I can switch to TwinMesh only to see how it looks like. So the way in TwinMesh is really easy. You start your project choosing what is the type of machine. So we have different types here. You can select this type of machine, and then the first step is to import the geometry. So the geometry represents the rotor profile or also the casing. In this case, it's only the rotor profile. And this rotor profile comes out of your 3D CAD model. So you can select the profiles in your CAD model, say export to IGES, and then you can use this IGES file to import this rotor profile into TwinMesh. It's also possible to use CSV files. So if you have an Excel sheet which is generating these profiles, then you can also import this one. The next step is to specify what is the what does this curve mean? So this is rotor wall curves R1. This is rotor wall curves R2. And the casing curve is not included here. If you have a circle representation of your casing, then TwinMesh can generate this casing curve on the fly. So I can specify the casing diameter. I can specify, but I have also changed the correct position, 180, and then it works. You have to specify the number of lobes for R1 and R2. So 3 lobes. And then depending on your imported geometry, could be that there is no gap. As I said, in TwinMesh, we need a gap. You can do these changes in your CAD model, or you can add here in TwinMesh an offset, for example, of 100 micron. And then you will get here a distance, so a gap size between the rotors and also between the rotors and the casing. Then the next step is to generate an interface curve. This normally is automatically while the meshing is run, but in this case I will show only how it looks like. Oh, not all, only the first one. So it's faster. And what I here can define at the beginning is how many meshes you need. For example, in this case, we have a pitch angle of 120 degree. If I want to have 1 degree angle step, then I have to change this value. So then you will get 120 meshes, which lead to a 1 degree angle step. Generate current interface again, because I've changed this number of meshes value. Okay, then the next step is to generate the mesh or define the mesh parameters. You can define it globally here in mesh generation, for example, 3 millimeter size. You can also increase the number of elements at the interface. You can specify how many elements you want in radial direction. As I said, 20 is the standard value here. And a lot of more, but these are the main settings. And then you can check how the mesh is generated. I will do it only for the first. Okay. This is... I've changed not the elements in radial direction, I've changed the elements in Z direction. That's why we have only this one. So now we'll get in radial direction. You can also change the boundary layer. So if you want to refine the mesh along the wall, then you can specify a first element height here. And as I said, if I zoom in, you have 20 elements along the gap. Then you can check the quality of the mesh. Or if you want, you can also manually change the node position if you want, if you have difficult profiles, if this is necessary, but the standard will give you a good mesh. Okay, so that's all for this one. Normally after this, you have to generate all the meshes for each rotational position. In this case, we have only generate the mesh for the first position because it takes some time, I think 5 or 10 minutes. I will open a final project where you can see how it looks like. So here in this case, I have a mesh for each rotational position. If I have every single meshes, you can also view it. And in this case, I also included also the actual gap meshes. So you will get a mesh for every for the whole working chamber, and all connected meshes, inlet, outlet, will be later added to the CFD solver setup. Okay, then you can check the 3D mesh quality and so on. And then after generating all the meshes, you can come to the CFD solver setup. Here you can choose the solver, CFD solver you have, which type of simulation, what are the connected meshes, inlet and outlet, what is the revolution speed, what's inlet outlet pressure, as I said, and some settings for the solver themselves. And then depending on your solver you have selected here, after the export of all meshes or the setup, the solver will start and start also the macro for defining all settings in the CFD setup. So these are importing the meshes, defining the physics, defining all the interfaces, defining plots, defining scenes to see what happens in this the solver. And so this takes some seconds here. So it's only running a macro to do it. Okay, so wait some seconds. Okay, I can show you how it looks like. So not only the setup is included, but also the post-processing. Okay. Okay, now he has imported all the meshes. So the stator meshes, the gap meshes, and the rotor mesh, and now only the physics and plots are defined.
Jan, how many cores are you using right now?
So in this case, only 5 cores on my local PC, but yeah, you can use many cores you want. It a little bit depends on your size of your mesh. So in some situation, it makes no sense to use hundreds of cores if you have a really small mesh. So that's why you have to check, okay, there is a good balance between the mesh size and the CFD cores, the cores you want to use. Okay, so as you see, a lot of scenes where you see the flow field, a lot of plots where you can see what is the mass flow inside, what is the pressure, what is the temperature, and so on. And then you can start your simulation run right after exporting. I hope I will have exported all the meshes here in this case, but I think so. Yeah, and then the solver starts, and the advantage in STAR-CCM Plus is that you can see the results for each time step or each internal step on the fly, so you can react if you have done some wrong settings and so on. So what we have here, pressure on rotors, is another predefined scene, but you can add the scenes like you want. You can set up automated animation generation. For example, if you do the run and you you want to see only the animations of a special view, then STAR-CCM Plus will generate only movies. Yeah, but you can also save all the local data. Okay, so that's all at the moment for this. If there are any questions, then
I saw another one, which is if the recordings will be available, which they will. On YouTube, we will upload the recordings so you can rewatch it.
yeah. So that's all from my side. Yeah, and if you have questions, you can contact us, and so we can answer your question.
Have a good week.
Okay, then thank you very much. Bye-bye.
Bye-bye.